Next is the principle of duality theorem. This is a very important principle of boolean algebra. This principle states that we just have to change the or sign to and the and sign to or, and 0 to 1 and 1 to 0. See, the dual principle of duality states that changing or sign to and sign, each plus in an expression is changed with a dot, each dot or the and symbol is changed with the or symbol, and in any of the places we have 0, that is interchanged with 1, and 1 is interchanged with 0. So, the derived relation using the principle of duality, and such expressions are called as dual of the original expression. So, any expression which is wherein we apply this principle to that particular expression, and such expression is called as dual of expression. Dual of original expression. Okay. So, the principle of duality theorem states that changing of plus, that is or sign to and sign, changing of and sign to or, and replacing 0 by 1 and 1 by 0, and any expression which is derived from applying this rule, we call it as dual of original expression. So, next we shall take the example. Take the postulate 2, the second postulate, that is the or relation postulates. So, first one, that is 0 plus 0 is equal to 0, 0 plus 1, that is 1, 1 plus 0 is 1, 1 plus 1, that is also 1. So, these expressions I am interchanging now. I am replacing the plus with the dot, that is or with the and, 0 is been replaced with 1. So, I am having 1 into 1, 0 is replaced with 1, plus is replaced with dot, again 0 is replaced with 1, equal to 0 is replaced with 1. 1 into 1 is equal to 1. Is it not true? It is true, and I told we should have both the values, or all the values must be true, only then the resultant will be true. Go for the next one. 0 is replaced with 1, plus is replaced with dot, 1 is replaced with 0, 1 is replaced with 0. 1 and 0. I am having and here, but it is 1 is 0. It means what? The resultant will be 0. 0 and 1 resulting to 0. Then again 0 and 0 resulting to 0. So, this is true. Though we applied the principle of duality theorem, these conditions or these expressions are not false. All these are correct. 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is also a 0. So, there is no harm in applying this principle of duality, and these are, see, now working according to the above relations, plus is changed to dot, 0 is changed to 1, but still the relations or the expressions are not harmed. So, these are the duals of this one. So, this is the original expression, and these are the duals. Next, we have some example there. Look at the table. Boolean expression x plus 0 is equal to x. So what can be the dual of this expression? X we will have like that only, because there is no rule to change the variables. We will only have to change the signs plus and dot with the and 0 and 1. X, the plus value is changed to dot, 0 is changed to 1 equal to x. So this is the dual of this expression. X into 1 is equal to x. The same way we have x plus 1, and there are many other examples also, you can go through that, wherein you can see only the or sign is changed to and sign is changed to or, and 0 is replaced by 1 and 1 is replaced by 0. Next we have a whole big set of boolean theorems. These are very important. We have many laws in them. We have involution law, the absorption law, associative law, the complementary laws. So there are many laws, and along with that we have a whole big set of boolean theorems. You can see it on the screen there. We have almost 22 theorems, and each one of them are proved. Each boolean theorem is proved, but how are they proved? How can you prove that x, suppose we have 0 plus x is equal to x. The first property or the first boolean theorem says that 0 plus x is equal to x. How do you prove that? That always 0 plus x is always equal to x. So we have to put some values to it. The same way we have in algebra also. If you have to prove an expression, we will have to put some values to the variables, and then we will have to prove. The same way we will have to put values to x, and then we will have to prove it. But what are the values we are supposed to put? We are supposed to put only two values, that is either 0 or 1. We can put the value of x to be 0 once and we shall prove it, and again we will put the value 1 and then we will prove the expression. And such type of proving is called as proof by perfection. So the method of technique of proving the theorem is proof by perfect induction. So we shall go for the first theorem now. First we have properties of 0 and 1. So in the properties of 0 and 1, we have 0 plus x is equal to x. This is the first theorem. So we shall take if x is equal to 0. First we shall take the value of x to be 0. So look at the LHS there. LHS is 0 plus x. What is the value of x? Value of x is 0. So I got the value 0. And what is RHS? X. X, what is the value of x? 0. So that is equal to the RHS. It is proved. When we take the value of x to be 0, what happens there? 0 plus x is the LHS. X value is 0. We got the value to be 0, wherein RHS the value is also 0. If x equal to 1, if I am taking the value of x to be 1, what happens? What is the LHS there? 0 plus x. 0 plus, what is the value of x? 1. So that is 0 plus 1 is 1. What is the value of x now? 1. I got the answer to be as 1 only. So which is equal to the RHS, and that is proved. This is how we prove, and this type of proving, the proving theorem by this method is called as proof by perfect induction. Next, we shall go to the second theorem. Theorem 2. 1 plus x is equal to 1. 1 plus x is equal to 1. So we shall take the LHS. If x is equal to 0. First we shall take the value. See, in Boolean algebra we have only two values, that is 0 and 1. So we are proving it by putting once the x value is put 0, then the x value is put 1. So we shall take the LHS 1 plus x. 1 plus x value is 0. What is 1 plus 0? That is 1. Alright. So we got the RHS. So LHS is equal to the RHS. Next, if x equal to 1, 1 plus x. 1 plus, what is the value of x? 1. 1 plus 1. See, 1 plus 1 you cannot write it as 2 because it is binary number system. 1 plus 1 means 1 or 1, 1 or 1 is 1. So that is nothing but the RHS. Left hand side and the right hand side. Left hand side is equal to the right hand side. This is how we are proving it. These are the two theorems how we proved. Next we shall prove the third theorem. The set of theorems are put up on the screen. You can go through that also. Along with that, I am also solving it out for you. 0 and x is equal to 0. So how do we prove this? If x is considered to be 0, we shall take the left hand side first. That is 0 into x. 0 into value of x is 0. 0 and 0 is 0. That is nothing but our right hand side. Next, if x equal to 1, LHS 0 into x, 0 into 1, 0 and 1, and both the values must be there, or all the values must be true, only then it will be giving the value 1. So 1 is 0 and that is 0 and that is nothing but our right hand side. So it is proved. Next, the fourth theorem. The fourth theorem states that 1 and x is equal to x. Again, if x is equal to 0, we shall take the LHS 1 and x. 1 and x value is 0. 1 and 0 is 0. 0, it is equivalent to x, and that is our right hand side. Our right hand side is x and that is having the value 0. Next, these four were the properties of 0 and 1, and these properties of 0 and 1 have been proved. Sorry, if x equal to 1, I am sorry, I just missed one part over here. If x equal to 1, one and 1, that is equal to 1, and that is our right hand side. So this was the properties of 0 and 1. We have proved all the four theorems of properties of 0 and 1. The next is idempotence law. Idempotence law, look at the notes over there. This law states that when a variable combines with itself using or and operator and the output is the same variable. It says that when a variable, if it is combining with itself using an or operator or an and operator. Suppose we have a variable x. X is combining itself with and or any of the variables, then the resultant will be the variable itself. In the notes I have given the proof using the truth table also. You can see beside that for the theorem 1 to 4 I have given the proof using truth table also. Maybe that is not much effective when you understand, but proving algebraically will be more effective. So in the idempotence law, that is the fifth theorem, x or x is equal to x. As the law states, when the variable combines itself with any of the and or operator, and the resultant will be x. So we shall prove this algebraically, that is by proof by perfect induction. And if you want, you can refer the truth table also, which is given in the notes there. If x equal to 0, we shall take the LHS. X plus x, 0 or 0. What is the value for 0 or 0? That is nothing but 0, and which is the right hand side. Right hand side is x, and that is nothing but 0. It is proved. This idempotence law we proved using if x equal to 0. Now we will have to prove if x equal to 1. I told you we will have to prove it by substituting the value for x as 0 once, and by substituting the value x equal to 1. That is LHS. We will consider the LHS again. X plus x, 1 or 1. Value for 1 or 1 is 1 again, and that is nothing but the RHS. RHS is x and the value is 1. So LHS is equal to the RHS. This was the fifth theorem. Next we have the sixth one, that is x and x is equal to x. X and x is equal to x, where the same way we are substituting the value x to be 0. LHS x and x, 0 and 0. 0 and 0 is nothing but 0, wherein we have the RHS to be x, the value is 0 because we have substituted the value of x to be 0. Next, if x equal to 1, now we are putting the value of x to be 1, where LHS x into x, 1 and 1, 1 into 1, or you can say 1 and 1, that is nothing but 1, where we have the RHS as x. So x value we have taken it to be 1. So LHS is equal to the RHS. After that, next we have the complementary law. So next is complementary law. This law states that when a variable is ANDed with its complement, it is equal to 0, and when the variable is ORed with its complement, then the value will be equal to 1. I repeat, this law states that when a variable is ANDed with its complement, variable is ANDed with its complement, then that will be equal to 0. And when a variable is ORed with its complement, and the value will be equivalent to 1. So this is the complementary law. The complementary law states that when a variable is ANDed with the complement of its own. You cannot have another variable here. The same variable's complement must be ANDed and the value will be equivalent to 0. And when the variable is ORed with its own complement, then the value will be 1. So how do we prove this? So we shall go to the proof. This is the 7th theorem. Theorem 7 says that x plus x dash, when you OR it, the equal value will be 1. So if x is equal to 0, LHS is x plus x dash, value of x is 0 plus value of x dash. X is 0 means x dash will be 1. 0 or 1 is nothing but 1. Next we have to take if x value is 1, putting the value of x to be 1. Let us take the LHS, x plus x dash, value of x is 1 plus x dash 0, then it is 1, then it is 0. 1 plus 0 is again 1, and which is equal to the RHS. So this was the first complementary law. The next one is the variable must be ANDed with its complement, then the value will be 0. It says that the value will be 0 if the variable is ANDed with its own complement. Then if x equal to 0, the LHS is x and x dash, value for x is 0, 0 and x dash. X value is 0, so x dash or x bar value is 1. 0 and 1, the value is 0. So the RHS was 0, hence the proof. Next, if x value is equal to 1, x into x dash, that is the LHS, x value 1 and 1 bar is 0, 1 and 0 is 0, which is the RHS. So this we have proved when the variable is ORed with its complement gives the result to be 1, and that is proved with x is equal to 0, and it is also proved with x equal to 1. And again, when a variable is ANDed with its complement, then it gives the answer 0, and that also we have proved using the value for substituting the value for x to be 0 and substituting the value of x to be 1. So this was the complementary law. Next we have involution law. Next is the involution law. This law states that when a variable is inverted twice is equal to the original variable. See, when a variable is inverted once, okay, and the variable is inverted again. So if a variable is inverted twice, then that will be equivalent to the original variable. So how do we prove this? We have only one expression, one variable over here. So it is like we take if x equal to 0, x dash and dash, which means that x dash and again that is complemented. Okay, so x value is 0, 0 is complemented once and it becomes 1, and again if it is complemented it becomes 0. So x double dash means first the value of x will be 0, then it will become 1 with 1 inversion, then again if it is inverted and it will get back to its original value. Please look at the proof of the theorem there. If x is equal to 0, then x dash is equal to 1, and again if it is complemented and it will take the value 0. So x double dash, or we call it as x double bar. So x double dash is always equal to x. The same way if we take x equal to 1, if I am taking the value of x to be 1, x is taken, it is inverted once and again it is inverted twice. X value is 1. Once it is inverted, it becomes 0. Again the 0 is inverted, it takes the value 1. So x, if it is inverted, any variable if it is inverted twice, then it will take its original variable value. Next we have commutative law. Commutative law, which says that this law states that the order in which the two variables are odd or ANDed, which will not make any difference. The order in which the two variables are ANDed or odd. The law says that there are two variables, x and y. The order in which it is ANDed, it will not make any difference. Y into y and x, or x and y is equal. It is ANDing x or y or x, it doesn't make any difference. So let us prove this using proof by perfect induction. That is the 10th theorem there. We have x plus y is equal to y plus x. This is the LHS and this is the RHS. Here what we do is, we are proving x plus y is equal to y plus x. So here we are taking the value for y. If y is equal to 0, LHS x plus y x, or the y value is 0, that is equal to x. This is the LHS. We shall take the RHS now. Y or x. Value of y is taken to be 0. 0 or x, x. So we have LHS is equal to the RHS. Here you can take the value of x also to be 0. If you take the value of x to be 0, this will be 0 plus y. You get the answer of LHS to be y, and here what happens? Y plus x. You can have y plus 0 and you will get the value y. This is also possible. You can take the value of x to be 0, or you can have the value of y to be 0. In the notes I have taken the value of y to be 0 and 1. Next we have the theorem 11, the 11th theorem, that is x and y and x. X dot y and y dot x, or you can say x and y and x, and it doesn't make any difference. So again here also we shall take the value of y to be 0. LHS x and y, x and 0, x and 0. X I have a value, the other value is 0, then it will obviously be 0. If y equal to 1, sorry, we should prove the RHS again. Once we prove the LHS, again we will have to prove the RHS. Then y into x, y value is 0 into x, 0 and x is 0. So the LHS is equal to the RHS. So next we will have to prove if y equal to 1. If the value of y goes 1, x and y, x into 1, the value is x, 1 into x, it is x. We have the RHS and the LHS equal, therefore x and y or y and x doesn't make any difference. The same way we had here x plus y and y plus x. You take either 0 as a value, you take 1 as a value, it will always give the LHS to be equal to RHS. And you don't have to take always y only as the value. You can also take x to be 0 and you can also take x to be 1. Only that is, we will have to ultimately prove that LHS is equal to the RHS. So anyhow you take, you will be getting the right answer. Next, theorem 12. So this says that if you do, while in ANDing, if you are ANDing these two and then you are ANDing with the x variable, and that will be equal to if you are ANDing these two variable and you are ANDing with the third variable. So anyhow, wherever the brackets are, you will be getting the same answer they say. But how do we believe that this theorem is true? If we are ANDing these two, suppose we have 1, 2 into 3, 3 into 2, 6 into 1, you get the value 6. Again here 1, 2 and 3, 1 into 2 is 2, 2 into 3, again you get 6 here. That is true, but we don't know that in the variables also it holds good, because this is with the algebra. Does it hold good with the boolean numbers? So we will have to prove it using proof by perfect induction, wherein we shall take the LHS first. So before we take the LHS, we shall take the value if y value is equal to 0. If I am taking the value of y to be 0, please look at the notes over there, where if y equal to 0, then LHS will be x in and y and z, x into y value is 0 and z, x into 0 and z is 0, 0 into z, anything which is multiplied by 0 is 0, x into 0 again it is 0. So we got the LHS value to be 0. So we shall prove the RHS. RHS we have x and y and z, x and 0 and z, x and 0. What is x and 0? It is 0 and z, z and 0, z into 0 is 0. We got the LHS and the RHS to be equal. Therefore, this equation will hold good. So next, we shall substitute the value of y to be 1. What happens when we substitute the value of y to be 1? So wherever we had y, we will take 1. 1 into z will give you the value z. X into z, the value will be x z. So here we don't get the LHS to be 0. If you are substituting y to be 1, we get the LHS value to be xz. The same way, if we are getting the same value in RHS also, then the theorem is proved. Here x and 1, x and 1 is x, again x and z will be xz. So we got the answer of the LHS and the RHS both to be same, and therefore this theorem is proved. We have substituted the value 0 once, then we substituted the value 1 also, and at both the cases we got the LHS and the RHS value to be same. Next, the 13th theorem. Here also the same procedure as that of AND, we just have OR in between. What happens if we OR these two variables first, and then if we are ORing with the x, or if we are ORing the x and y together first, and then we are giving the OR value z later on. So if y equal to 0, first we will substitute the value of y to be 0. Let us take the LHS, x plus y plus z, x plus y value is 0, the bracket is important there, 0 plus z. So 0 or z, if I am saying or, any one is there, then the condition is satisfied. Then it is x plus 0 plus z is z. So this is the resultant of the LHS. This is the resultant of LHS. Then we have RHS, x plus y plus z, value of x, value of y is 0 plus z, x plus 0 is nothing but x plus z, and that is equal to x plus z. So the LHS and the RHS come same when we have the value of y to be 0. What if I am taking the value of y to be 1? Let us consider the value of y to be 1. When I take the value of y to be 1, it is 1 plus z. What is 1 plus z from the property of 1 and 0 and 1? From the properties of 0 and 1, we know that 1 plus x is equal to 1. So therefore, x plus 1 plus z will be equal to 1. Again, from the properties of 0 and 1, please turn back and look at the properties of 0 and 1 if you want. We have 1 plus x giving the value to be 1, that is x plus 1 will be equal to 1. So that is the properties of 0 and 1, and that is already proved. We have already proved the properties of 0 and 1, and so those properties or those theorems we are making use here also. Again, if I am taking x plus 1, and that will be giving you the value 1. So LHS is 1. Next, I am taking the RHS, x plus 1 plus z. X plus 1, from the properties of 0 and 1, we infer that x plus 1 is nothing but 1, 1 plus z. So again 1 plus z is nothing but 1 again. So our RHS is equal to our LHS. Therefore, we take the value of y to be 0 or we take the value of y to be 1, we will be getting the value of LHS and the RHS to be equal. So this was up to our commutative law. Next we have distributive law. Distributive law allows the multiplying or factoring out an expression. What does distributive law says that we can factor out, we can take the common factor outside and then we can have the multiplications or the evaluation of the expression being done. So that is the 14th theorem. X and y plus z is equal to xy plus xz. This we have already learnt in the algebraic calculations, that if any variable is put outside the bracket and this can be multiplied, x into y plus x into z. We know that it is a theorem and it is there for our algebraic equations also. But boolean, how do we prove it? So we are proving it by putting the value of x to be 0 or 1. So here also the same way we shall prove the LHS and the RHS. We will derive the LHS first, then we will derive the RHS, and we will prove that those two are equal to each other. So now first let us take if x equal to 0. If x equal to 0, the LHS x into y plus z. Here we have 0 and y plus z, 0 and y plus z. We shall take y plus z as a single variable, 0 as another variable. 0 and anything will always substitute to, it will always be equivalent to 0. We will take the RHS now. xy plus xz. Value of x is 0 and y plus 0 and z. 0 and y is 0 or 0 and z is also 0. 0 plus 0 or 0 is always equivalent to 0. So the value of LHS and the value of RHS come similar, and therefore it has been proved with the value x equal to 0. So now let us see what happens if I am taking the value of x to be 1. I shall take the value of x to be 1 into y plus z. So since we considered 1 as another variable and y plus z as another variable, 1 into y plus z, anything which is multiplied by 1 is itself, so it is y plus z. Same way we shall consider the RHS. X value is 1 into y plus 1 into z. 1 and y is nothing but y plus 1 and z, nothing but that is equal to y plus z. So we got the answer in the LHS to be y plus z. Here also we have the value y plus z. So this is proved with x value to be 0 and also the x value to be 1. Next we have another theorem with the same distributive law where we are taking the common factors outside. This is an important theorem. They will ask you for the exam like state and prove the distributive law, and they will ask you to prove this particular theorem. It is an important theorem, I can say. X plus y into x plus z is equal to x plus y z. Here we are not taking the LHS separately and proving it to some value, or RHS to be taken into some value, and it is not proved like that, or neither we are putting any value to x and y. We are proving it by using the other theorems which we have already studied. So first let us take the LHS. And after solving we will get the result as RHS only. The RHS we will be getting as the result. So first You can go through the notes which is there also, and along with that please listen to what I am saying. X into x, this can be multiplied and this can be multiplied. This we know, this has been there in our high school sections also. X into x plus x into z. Then again y into x and y into z plus y x plus y z. Once we multiplied x into x, x into z, we got y into x and y into z. So let us rearrange it properly. X plus xz plus yx, I can write it as xy plus yz. I have rearranged it. Now I know x into x. From a property we know that x into x is equal to x. When you AND or a variable by its own, then the resultant will be the variable itself. This we have already proved in the previous theorems. So what happens now? X into x will become x plus xz plus xy plus yz. X and xz. Can I take the variable x outside since it is common in both the terms? So x I am taking it outside. What is left here? 1 plus z plus xy plus yz. What is 1 plus z? In the previous theorems we have proved that 1 plus z is, or 1 plus x is nothing but 1. Therefore x into 1 plus xy plus yz. So here we are making use of the theorem 1 plus z is equal to 1. 1 plus z is equal to 1. So we have x plus xy plus yz. Again we got two terms here, x plus xy. Here x is common. If I am taking the value x outside, 1 plus y is left out and yz is there. So 1 plus y is nothing but 1 again. 1 plus y is y. So x into 1 plus yz, and that is equivalent to x plus yz. I repeat, if you want I shall repeat it again. This is our theorem. We will have to prove this. X into x plus y into x and x into x plus x into z, again y into x plus y into z, x into x plus x into z plus y into x plus y into z. This is the term we get. Hope you know this. This is same as you how we do a plus b into a plus c. We will multiply these two, this with this and this with this. Again we multiply this and we multiply each term with the another term. So we all know x into x is nothing but x, that is the previous theorem which we have already proved. We get the value to be x plus xz plus yx, I can write it as xy. That is just for our convenience, and we have already proved that if the order changes and it doesn't make any difference, x into y or y into x, it doesn't make any difference. Next, yz. Here I am taking the common outside. Here x is there. Here also we have an x. So we are taking out the common. If I am taking x outside, inside the bracket, here there was x. I have taken it outside. Then what is left? 1 is left there. 1 plus I have taken the x outside. What is left? Just z plus xy plus yz. 1 plus z is nothing but 1. This we have also proved previously. This is all there in the properties of 0 and 1. X into 1 plus xy plus yz. X into 1 is nothing but x plus xy plus yz. Here again in these two we can take the common term outside. We are taking the x outside. We have 1 plus y plus yz. 1 plus y is nothing but 1. X into 1 plus yz, that is x plus yz, and which is nothing but our RHS. Hope you understood this. That is why I have done it twice. You can look at the printout also and you can see through. Each step has been put in there, how we do it and what is taken outside and through which theorem we have done. So x into x, this is very important, x into x values to be 1, sorry x, and we are taking the common term x outside, and what is remaining is 1 plus z. 1 plus z is nothing but 1, and this is from the properties of 0 and 1. Then again we have taken x outside in this term, wherein 1 plus y we get, again 1 plus y is nothing but 1, and we finally we reach to the RHS. Next we have absorption law. Absorption law enables a reduction of complicated expression to a simpler one by absorbing the common terms. So what does absorption law makes is, there is a complicated expression out there and it will make the expression to be very simpler by absorbing the common terms. Thus even we did the same over here also. We have absorbed x from both the terms. We absorbed x outside and only 1 and y is left out. So this is what the absorption law says. This is the 16th theorem. I have given all the numbers for each of the theorems. Totally we have 21 theorems, you have seen in the notes previously, because it is easy for us to note down which theorem number it is, and it will be helpful for us while learning it for the examinations also. So next, the 16th theorem. From 16 to 21 we have 6 theorems, and all those theorems comes under the absorption law. So first one is x plus xy, that is equivalent to x. This is the 16th theorem, wherein we are proving it the same way, but not by substituting the x value to 0 or 1. We are simply simplifying it using the algebraic equations. X plus xy I am taking. I can take the x common outside because they are the common terms there. X, if I am taking it out, what is left in with this term? Only 1 is left, plus x is taken outside, only y is left out. So x into 1 plus y is nothing but 1. So x into 1 is x, which is our RHS. So when you are proving like this, you don't have to substitute the value for x to be 0, or we don't have to substitute the value of x to be 1. We just have to simply absorb the common terms there, and we shall arrive at the RHS. Next, 17th one, x into x plus y is equal to x. So x into x plus y is equal to x. We have the LHS. So we don't have to absorb the common terms, but we will have to multiply it because it is not a proper term there, proper expression there. X into x plus x into y, x into x and x into y, and we all know that x into x or x dot x is equal to x. That is, we have already proved, that is our basic boolean theorem only. So x plus xy. At this point I think I can take one common term outside, which is x. If I am taking the common term x outside, then it is 1 plus y. Again we know 1 plus y is nothing but 1, and we arrive at the RHS. Finally, we arrive at the RHS. Always remember, we will have to see whether there are two terms which are been ANDing by itself and which will result in the variable itself, and then if any common terms are there, that must be absorbed, and whatever is rest inside, that must be applied with some of the theorem. 1 plus y, we know it is 1, and we arrived at the RHS. Next, see, xy plus xy dash is equal to x. Here what we have to do is, we have used a complementary function over here. We have to solve this expression so that we get the answer to be x. So here we have x, let us take the LHS, xy plus xy dash. I can see the common term x over there. If I am taking the x outside, y plus y dash is left out. So from the Boolean theorems, we know that y plus y dash is nothing but 1, and y and y dash is 0, but y plus y dash is 1. So x into 1 is nothing but x, and we have arrived at the RHS. This is one of the Boolean theorems. You can turn back and you can see y plus y dash or x plus x dash is nothing but 1. Next we have the 19th theorem. X plus y into x plus y dash is equal to x. Here we don't have to absorb anything, but we will have to multiply things there. The same way as we did for the 15th theorem. Always make a habit of putting such arrow marks so that it will be easy for you when you are learning or also when you are solving. X into x plus x into y dash plus y into x plus y into y dash. X into x, we have our theorem that is corresponding to, x into x is corresponding to x plus xy dash plus xy plus y into y dash. Y plus y dash is equal to 1, y into y dash is corresponding to 0. This you can refer the previous theorems. We have already proved that y into y dash or x into x dash is equal to 0. Here, since the y into y dash goes to 0, we have a common term here. With 3 terms we have the common variable x. So from 3 of the variables also we can take the x outside. We don't have to consider only 2 expressions here. We will have to consider all the 3, because in all the 3 the common variable is x. When I take the common variable x outside, 1 plus y dash is left here plus y is left. So y dash plus y dash into y is 0, y dash plus y is 1. So, x into 1 plus 1. So, 1 plus 1 is not 2 because it is boolean algebra. We have 1 plus 1 to be considered as 1. X into 1 and we arrive at the RHS which is equal to x. Always remember, if there are common terms in 3 of the expressions, if there are 3 common, then we will have to take the value x from the 3 parts of it. Next, this is the last boolean theorem. We have x into x dash plus y is equal to xy. So, what we do here is we simply multiply the terms there. This into this and this into this. We have only one term outside, so we have to multiply this term with this and this one with the x with the y and x with the x dash. X into x dash plus x into y. We already know x into x dash is nothing but 0. 0 plus xy is nothing but xy, which is our RHS. These are the 21 boolean theorems which we have in your curriculum, wherein all the theorems up to 14 theorems you prove it by proof by perfect induction, and later part of that you will have to prove it algebraically by either absorbing it or by using the previous theorems. Previous theorems once we have already proved, and then that can be used in the proving these theorems from 15 to 21.